Welcome back. This is Terry Donovan, and we're here on this video to pick up where we left off with our spreadsheet from the first video and include those calculations that Jed mentioned so that we can really get a handle on what this equilibrium number of patches means and also get a good intuition for how it feels. We're back to our landscape now, and just to refresh your memory, our model inputs are in green. We can specify the size of our landscape by entering the number of rows and the number of columns, and the area in red or pink is given a number 1 if those are the 16 cells of interest. So the total number of patches in the system is 16. And of course you can change these entries and quickly change the size of your metapopulation. We're going to enter the number of years under consideration, and that goes in cell B8, and we'll consider a maximum of 25 years. You can change this at a later time as well. We've set the probability of local extinction to 0.7, and we also need to include the probability of local colonization, and Jed talked about that in his last video. Let's set that to be 0.6. We'll be able to very quickly change these two very critical and important parameters and then see how these two numbers affect the fraction of patches that are occupied over time. Now here's where we're going with this. This is the landscape of interest. We start off with a population of being occupied or unoccupied in year T. So T can represent our initial year, 0, and just to seed this with occupied or not, we're going to enter an equation that uses an if function. And the if function is going to draw a random number, and if the random number is less than 0.5, we're going to have the spreadsheet return the number 1, otherwise we'll have the spreadsheet return a 0. We'll drag this all the way over and down, and even though our landscape consists of only 4 by 4 or 16 cells, we're going to copy this equation all the way across, and remember though that we're focusing really on these 4 by 4 cells. So you'll have to imagine that these are no longer come into play, and I'll show you how we're going to deal with that in just a second. So these are color-coded so that if the site is occupied, it receives a 1, and if it's vacant, it receives a 0. So in this particular landscape at time t, which we've just seeded with a random number, in this cell here, we're going to now calculate the number of patches that are occupied. And to do that, we're going to select cell Z13, and we'll use a function in Excel called the SUMIF function. Let's find that function and open up the dialog box. This is a handy function because it really lets you sum things according to rules that you specify. This first argument is called range, and we're not going to use this grid, we're going to reference this grid, our metapopulation grid. So our range is E3 to N1, and our criteria is the number 1. So we're basically telling Excel, we're going to consider this whole range, but we only want to consider those cells that have the number 1 in it, which is our criteria. Now if these cells have the number 1, the sum range tells you what to sum. And here we're going to select this entire grid at time t, and you'll see that Excel returns the number 11, meaning that 11 out of the 16 patches were occupied in year 1. We can now compute the fraction of patches as the number of patches that are occupied divided by the number of patches in the system. So we're starting off with a fraction of patches, that's 0.6. And you'll notice that I seeded this with random numbers, and if I press F9, I'm going to get a different starting place. And we really want to copy these and then paste the values right over the top so that this is fixed, and this is the fixed condition in year 0. Now, don't worry, your random numbers will certainly look different than mine, and your pattern will be different, but that's okay. For the random numbers that I happen to draw, I'm starting with a population in which there are 8 cells, or 8 subpopulations are currently occupied in year 0. And the fraction of patches is 8 out of 16, which is 0.5. So it's just saying what proportion of these patches are occupied. And that number would be calculated and entered right here. So we'll go ahead and enter it by hand and indicate that that's our starting population size. Now here is where the rubber meets the road. In this cell, P16, we're going to enter our model equation for metapopulation dynamics. And we're going to use the exact equations that Jed mentioned in lecture. First of all, if the patch above, so this particular patch corresponds to this upper left corner patch here, if this patch was empty and unoccupied, we're going to let it become colonized if a random number is less than the probability of colonization. That's given in cell B12. Hopefully that makes sense. If it's empty, then 60% of our random numbers should result in that 0 flipping over and becoming a 1 in the next time step. If, however, the patch is occupied, such as in Q2 here, or Q3, what we would want to do is say, we'll let that patch go extinct if a random number is less than or equal to 0.7, which is entered in cell B9. Now you can probably guess that we need to consider both of these conditions. It's either 0 or it's 1. If it's 0, we're going to have the spreadsheet conduct one set of equations, and if it's 1, we'll have the spreadsheet conduct another set of equations. So we'll be doing multiple if functions. They'll be nested into each other, and it won't be as difficult as it seems. So the first test is going to be if this cell P3 is equal to 0. That means it's empty in the time step t. It is. Then if it is, then we're going to ask now if a random number is less than the probability of local colonization. We're going to let that population become colonized. Otherwise, we'll let it stay vacant. So that if function is going to go right here. So we're asking, is it empty? If it is empty, a 0, then we're going to ask about colonization. If it's not empty, it has a 1 in it, and then we're going to ask about extinction. So this is going to have an if function as well as this argument. So we need 2 more if functions nested in here. And we can nest those by heading up to the left side, finding if, and this opens up a second dialog box, and this is in fact dealing with the first case where the patch is vacant. So we're going to now ask, is a random number less than or equal to the probability of local colonization? We'll anchor that reference, and if it is, then we'll say that the patch becomes occupied, it's colonized, and now returns the number 1. Otherwise, it stays vacant and we have the spreadsheet return a 0. We press OK, and now we have to head back up to our first if function. So we'll click on that first if, open it up again, and you can see here that there is the second function we entered. That's the one we just entered. So if the patch is unoccupied, we're going to ask if a random number is less than the colonization probability. If it is, we'll call that patch colonized and return the number 1. Otherwise, we'll keep it empty and return the number 0. If the patch is not 0, then it must be 1. It's occupied. And in that case, we want to draw a random number, and I'll just type this in here, and if this feels too uncomfortable for you, of course you can go back and use and open up a new if dialog box. Here though we'll say if a random number is less than or equal to the probability of local extinction, anchor, then we'll have the spreadsheet turn that 1 into a 0. Otherwise, we'll keep it at 1 and the population will persist. We need to anchor the reference to B9. We press OK, and that is our metapopulation model. Really, right here is the key equation that's generating our dynamics. We have a different formula for those patches that are currently occupied from those that are currently unoccupied. We can carry this equation through and then down. And what we've simulated now are the dynamics. So this population right here was empty, and it stayed empty. This one was present in year t, but it went locally extinct. This one was unoccupied in year t, but it becomes colonized in year t plus 1. We want to track this through time, and so just as we did up here, we're going to enter a SUMIF function to count the number of cells that are occupied in year t plus 1, and then count the fraction of patches. Let's find that SUMIF function again. And remember, the SUMIF function has three arguments. The first is the range, and we're only going to consider those that have the number 1 in it, and then we will choose for our sum range the cells in year t plus 1. And then the fraction of patches is calculated as the number of patches that are occupied over the total number of patches in the system. And what we see here is we started off with 8 patches that were occupied. The fraction of patches was 50%. 8 of 16 patches were occupied. In the next time step, we still have 8 patches that are occupied, and the fraction is still 0.5. However, the patches have winked in and winked out, as Jed has described. Some patches that were previously empty were now colonized, and vice versa. And if we press F9, we'll get these changing dynamics, and each time drawing a new set of random numbers. These represent new possible results for this particular metapopulation. Now the next thing we want to do is to simulate this not just for one time step to the next, but to simulate it down through all of the years in consideration. We said we'd be looking at 25 years, and we are going to run this model through to the year 25, each time tracking what is the fraction of patches in a particular time step. Now this first one is hard-coded in. I hard-coded mine in, and I ended up with 8 patches occupied. You might have something different. In the next time step, though, we draw random numbers and we get a result, and what we want the spreadsheet to do then is to copy this value in cell Z27, search down column AB and find the next blank cell and paste it in there. Then we want to take this landscape, this pattern of occupancy for year t plus 1, and paste it directly on top of year t. This becomes our year t, and then we let the metapopulation equations now work on that new pattern of occupancy. Hopefully that makes some sense. We're going to use a macro to do this, and the first thing we want to do in our macro is to turn our automatic calculation to manual so that we can control exactly when the spreadsheet calculates. We're going to go to the Macros button, and we're going to choose Record Macro and press OK. And this is just called Macro 5. We'll add a button to this in just a second. Yours might be called Macro 1. So the first thing we're going to do before we do anything else is we're going to go to the Formulas tab and turn our calculation options to manual. This means we need to press F9 to get the spreadsheet to calculate and generate these random numbers when we want them to be generated. So the first thing we're going to do then is press F9 and get a new set of random numbers. We're going to copy the fraction of patches that are occupied in this year t+1, and we'll go up and we'll copy that. Then we'll select cell AB1 and we'll find the next blank cell. So we'll find, and when this dialog box pops up, we're going to expand the dialog box and we're going to search down the columns and we're going to find the next blank cell. So leave that part blank and then choose Find the next blank cell. And then close. And then we're going to paste the value in. So it's pasting in the value that was right there. So 0.4 was really 0.375. It's just not displaying the decimals here because we've shrunk the column so much. We're not done yet. Now we need to copy this landscape and click on cell P3 and then once again paste the values in. So what we've done now is we've just pasted in this landscape into year t so that when we run our macro the next time, the instructions will be carried out exactly as we have recorded them. The macro will press F9, it will record random numbers, a new landscape pattern will be generated in terms of patch occupancy. We'll take the fraction of patches occupied and we'll store them down the next empty cell, at the next empty cell. And then we'll take this pattern and we'll paste it into year t. At this point we can stop our macro and we can add a button to our spreadsheet to simulate these dynamics through time. And you can choose any kind of symbol or button that you'd like to. So if we choose a little star here, I can tag this star to the macro that I've just created. Mine's called Macro 5. And now if I press this star, we're going to be simulating these dynamics through time. And as we do this, you can see that we are tracking the fraction of the patches that are occupied with every single year. And we've set up this graph so it's just automatically adding these series in. And for this particular set of numbers, we end up with a final fraction of patches around 0.6. And you can see that for these numbers, 0.7 is the probability of local extinction, 0.6 is the probability of local colonization, that this metapopulation is persisting through time. If it were to go extinct, we'd see this line fall down and go to the 0 and perhaps come back to life again, and that is a very interesting thing that we'll cover in the next video. You'll never see the fraction of patches expand beyond 1 because we're dealing with a proportion, and proportions for this particular problem don't go above 1. It's impossible to have more than 16 patches occupied. Now in lecture, Jed mentioned that we can actually calculate the equilibrium number of patches that are occupied, and that's a combination of our two key parameters, the probability of local colonization divided by the probability of local colonization plus the probability of local extinction. And really that's just giving us a ratio. So we'll enter that in cell B15, the probability of local colonization divided by, open parentheses, the probability of local colonization plus the probability of local extinction. And we end up with a number of 0.46. Let's go ahead and hide some of those decimal points. So under these conditions, probability of local extinction and the probability of local colonization, we end up with this equilibrium fraction of patches that are occupied of 0.46. And if we stretch this out, we can try to find where 0.46 is. It's roughly right here. And you'll see that this number bounces up and down. And that is because our system is pretty small here. It's really small. It doesn't look too small. It's 16 patches. And if our metapopulation was infinite in size, we would see that over time this number would become much more apparent than it is with the fairly small system that we've depicted here on the spreadsheet. Now it turns out that this equilibrium number of patches is simply a combination of two other parameters. These two right here, local colonization and local extinction. And it would be helpful to know if we let these vary between 1 and 0 at each and every possible combination to calculate the equilibrium number of patches occupied. And we've done that by setting up another section of the spreadsheet. And I bet you feel another data table coming on here, and you'd be right. So we'll hide these cells, and incidentally, to unhide them, you could select over column B and AD, and then double click, and it will expand all of your columns back again. Now in this case, here is the grid of cells we want to look at. So I'm going to move our spreadsheet over a little bit more. And here, it's hard to see. I'll make these bold in an attempt to make them more visible. But here we have the probability of local colonization, PI. And down this column, we have the probability of local extinction, PE. Here, in this cell, we entered the exact same equation we just entered. It's the probability of local colonization divided by the probability of local colonization plus the probability of local extinction. So that sets up the data table. Then, to add the numbers in, we'll go ahead and select the entire table, starting with the cell in blue. We'll go up to the Data tab, and we'll choose What If Analysis and Data Table. The row inputs are going to go into cell B12. That's where we're storing the probability of colonization. And the column inputs, the probability of local extinction, are going to feed into cell B9. And if we press OK, now we have to press F9 because we're still in our calculation mode. And in fact, let's go ahead and get out of that. That's in Formulas, Calculation Options, Automatic. And we'll go ahead and format these so that they look a little bit better. These are numbers, and we'll display 2 decimal points. And then once again, let's go ahead and format these with some conditional formatting so that the fraction of patches occupied is highlighted, and we'll choose green for meaning high numbers and red meaning low numbers. So here's the probability of colonization, and here is the probability of local extinction. If local extinction is low, then as long as the probability of colonization is somewhat high, we can still be in this green area here. And this is the equilibrium fraction of patches that are occupied. For example, if the probability of local extinction was 0.2 and the probability of colonization is 0.7, then our fraction of patches that would be occupied under equilibrium, so if we had a very, very large metapopulation, we would expect that 78% of the patches would be occupied over time, even though which patches are actually occupied is constantly changing through time. In contrast, when you see that the colonization rates are low, then if the probability of local extinction is high, then we're at a point where the equilibrium number of patches is also very low. These characteristics, as Jed mentioned, these are things that are governed by a species. How mobile is the species? What is the landscape like that allows colonization to occur? Those kinds of things influence this probability of colonization. And likewise, probability of local extinction is also governed by many factors. And so the idea here would be that you would find the species of interest in this grid and try to determine what values here characterize a particular species, and then use this grid to help you determine what this equilibrium number ought to be. Just as we graphed up here, we've already graphed these out in a line format. You can explore that more on your own. And now let's head back over to Jed. We've got some more things to explore with this simple metapopulation model, and we'll see you next time.